Welcome, everyone. Let's get started. Today, we are diving into a foundational pillar of machine learning operations, creating and managing data assets within an Azure Machine Learning workspace. Reliable models start with reliable data, and mastering data assets is critical to your success. Let's begin by defining what a data asset is. In an enterprise data science process, before you can run an automated machine learning experiment or any custom training script, you need to prepare your data. Rather than passing raw file paths around, you create a data asset in Azure Machine Learning. Think of a data asset as a highly secure, version-controlled pointer to where your data lives. Why is this important? Because it completely separates your compute logic from your storage layer. Data scientists never have to hard-code URLs or handle sensitive storage credentials in their scripts. They simply request the data asset by name. This practice shifts our workflow from messy, ad hoc experimentation to a secure, enterprise-grade engineering discipline that scales beautifully. Take a look at this diagram. It illustrates the basic lifecycle of a data asset. We start on the left with our raw data storage, such as Azure Blob. We don't move the data. Instead, we register it as a data asset. This registration process creates distinct, immutable versions version 1, version 2, and so on. These versioned assets reside logically within the machine learning workspace, serving as the clean, official input source for all of our downstream training pipelines. Now, having a pointer to your data is great, but how does the machine learning engine know how to read it? This brings us to the ML-teable format. In order for services like AutoML to understand how to read and parse the data, you need to create an ML-teable data asset that includes the exact schema. An ML-teable is created when your data is stored in a folder alongside a specific ML-teable YAML file. Why do we do this? It eliminates the guesswork. Instead of a data scientist writing 50 lines of complex data loading code in a notebook, the ML-teable explicitly defines delimiters, headers, and data types. This abstraction allows the Azure ML compute to instantly and flawlessly materialize your raw files into a usable tabular format. Here we see the internal structure of an ML-teable data asset. It all starts with a single data folder. Inside this folder, you place your raw data files like CSVs or Parquet files right alongside your ML-teable YAML file. The YAML file acts as the blueprint. When you register this folder, it becomes an official ML-teable data asset. Because the blueprint is attached directly to the data, the AutoML engine can parse it automatically without any manual intervention. Once you have structured your data, you must formally register it into the workspace. After you have created the data asset, you can easily specify it as an input for your ML jobs using the Python SDK. You do this by referencing its path, for example, path equals Azure ML my data 1. Why is registration so critical? It establishes a single, undeniable source of truth for your entire organization. It prevents data duplication and ensures no one is training models on outdated, local copies of a dataset. Furthermore, when you combine registered data assets with tracking tools like mFlow, your system logs the exact version of the data asset used for every single experiment. This guarantees complete auditability and reproducibility. Let's walk through the registration and access sequence. A data scientist uploads raw data to the Azure Data Store. They then register the data asset in the Azure ML workspace, defining its name and version. The workspace provides a unified URI. When the data scientist submits a training job, they simply pass this URI. The training job asks the workspace to resolve the URI securely and then mounts the data directly from storage. The user never handles the sensitive storage keys. Connecting your data asset is just the first step. The data must be clean. This is where data guardrails and featurization come in. Before training begins, AutoML automatically applies scaling and normalization to numeric data, which helps prevent large-scale features from dominating the model. You can also configure optional featurization to handle missing value imputation or drop high cardinality features like record IDs. Why? Because real-world data is rarely perfect. These guardrails prevent your training jobs from crashing. While this process is automated, it is completely transparent. The system will alert you if an issue was passed, done meaning it was fixed automatically, or alerted meaning you must intervene manually. This flowchart demystifies the pre-processing pipeline. Our registered data asset flows into the data guardrails engine. The engine simultaneously performs multiple checks. It checks for class imbalance, imputes missing values, and drops high cardinality features. These automated transformations yield a clean, featurized data set, perfectly primed for the final model training phase. To operationalize our models, we must move beyond single scripts and build pipelines. In Azure Machine Learning, a pipeline is a workflow where each task is defined as a component. You can pass a registered data asset directly into this pipeline as a job input. Why use pipelines? Because they allow you to automate multi-step logic like preparing data in step 1 and training the model in step 2. How does the data move? The output of your first component, say your clean data, automatically becomes a new data asset that is fed directly into the expected input of your second component. This chained approach completely eliminates manual handoffs and preserves a flawless data lineage from start to finish. Let's trace the data through a pipeline. We begin at the top with our registered data asset, serving as the pipeline job input. This feeds into step 1, our prep data component. Step 1 does its job and produces an output. That specific output data is seamlessly routed as the input for step 2, the train model component. Finally, step 2 outputs our trained, registered ML model. It's a continuous, unbroken chain of data. Data asset management is a core part of the overall solution architecture. We divide our MLOps strategy into 2 main phases, the inner loop for model development and data exploration, and the outer loop for continuous deployment and monitoring. Why separate them? To protect production. Data scientists need a safe environment to explore data assets without accidentally breaking live systems. Therefore, we set up distinct environments: development, staging, and production. Each environment has its own Azure ML workspace and its own approved data assets. We then use tools like GitHub Actions to safely automate the transition of code across these environments, ensuring jobs only trigger using the correct, environment-specific data assets. This diagram illustrates the MLOps loops. On the left, in the inner loop, data scientists safely explore the development data asset and train models. Once a model shows promise, it passes through CI/CD via GitHub Actions, where a pull request ensures human review before packaging. Finally, it enters the outer loop on the right, deploying to an endpoint where we continuously monitor live incoming data for drift against our original data asset. A major benefit of managing your data as registered assets is automation. Machine learning models degrade over time as real-world data changes. To combat this, we must continually retrain our models. Manual retraining is simply too slow for a modern enterprise. Instead, we enable continuous delivery by automating the workflow. We configure a GitHub Actions workflow that securely authenticates with Azure using stored secrets. When a data scientist updates the training code in a feature branch and merges the pull request, this action automatically triggers the Azure ML pipeline. The pipeline dynamically pulls the absolute latest version of our registered data asset, retrains the model, and prepares it for staging. Here is the automation sequence. A developer merges a pull request in GitHub, representing a code update. This immediately triggers GitHub Actions, which sends a command to the Azure ML workspace to start a pipeline job. The workspace automatically fetches the latest version of our data asset. The training job executes using this fresh data and reports the success back to GitHub Actions. Automation at its finest. Let's tie this together with a real-world use case. Prosware, a healthcare startup, built a classification model to predict diabetes based on patient medical records. Because disease factors shift based on geographical locations, the data science team must constantly update the model with new data segments. They couldn't safely hardcode raw data paths containing patient files into their scripts. Instead, the infrastructure team provided an Azure Blob storage connected to the ML workspace. Prosware registers this medical data as a secure ML-teable data asset. Now, whenever new patient data is added and the asset version is updated, their GitHub Actions automatically trigger a retraining pipeline. This end-to-end MLOps strategy ensures the web app serving practitioners is always powered by the most accurate, secure, and up-to-date data available. Look at the Prosware data flow. New regional patient data arrives and is securely stored in Azure Blob storage. It is immediately registered as a new data asset version. This update acts as a trigger for our GitHub Actions, which launches the automated ML pipeline. The pipeline trains a fresh diabetes model, which is seamlessly deployed to the practitioner web app, delivering life-saving insights instantly.